Before getting started, I wanted to give a brief overview of why I believe that data science is key to Uber's future. And this is really a combination of three factors coming together. Firstly, that we are a real-time business. That secondly is operating across the globe. And thirdly, we want to, of course, incorporate nuances of the various different marketplaces as well as product preferences of our end users. And in order to do this efficiently and effectively, there's really no other way than to leverage data science at scale. And so, unsurprisingly, Uber has heavily invested in data science from early stages on in the company, and now we have hundreds of data scientists working across the entire company to improve user experiences. So, given the importance of data science to the company, as well as the large number of people who are working in this space, we're continuously seeking to increase the innovation cycle and speed in this field, whilst improving accuracies of the various different data science models. And so today I'm going to showcase to you how we accomplish faster and more accurate data science results. At the beginning, our data team has heavily invested in building tools and platforms that empower us data scientists and data analysts. But we didn't stop there. As a next step, we wanted to empower everyone within the company and transform them at a push of a button into a data scientist, of course with best practices and guardrails incorporated. And to this end, we hired data science specialists, for example, in the areas of conversational AI, experimentation, anomaly detection, and many different other fields. And together with their cross-functional counterparts in engineering, product, and design, these teams build scalable tools and platforms that transform anyone at Uber into a data scientist. Now let's start out by looking at the four lifecycle stages of a typical data science project. It starts off with data exploration, followed by iterative prototyping. Once an adequate model has been found, it then gets productionized. And of course, during rollout as well as post-rollout, we want to carefully monitor any of these algorithms. Now this closes the first generation loop of any data science project, and there one can start anew if necessary. So the goal here is, of course, to speed up every one of these four steps of the project lifecycle. So let me show you some of the platforms and tools that our data team has built in order to accelerate this. Let's start with the exploratory phase. Data really is at the center of everything because without data, there is no science. And so in order to transform the hundreds of petabytes of data quickly and efficiently from data into knowledge, our data team has built various different tools around this, including a data book that surfaces and manages meta information about the data. On the right-hand side, you can see Kepler.gl. As you can imagine, at Uber, we have a vast number of spatiotemporal use cases that we're tackling. And so, of course, we want to visualize this data efficiently and very quickly. And to this end, our data visualization tool has built this data-agnostic, highly performant web-based application that can help us visualize very large spatiotemporal data sets at scale. We have also open sourced Kepler.gl about a year ago, where it has found a lot of followers. We have now over 35,000 Uber external users of Kepler.gl, and it has gathered over 5,500 GitHub stars. Now, when it comes to the development phase or prototyping phase, our data team has built what is known as Data Science Workbench. Think of this like an IPython Notebook++ that is deeply integrated into our data stack, allows for version control, share capabilities within the organization, and also most recently has been deeply integrated into our machine learning platform, Michelangelo, to allow for fast deployment of machine learning models. On the right-hand side, you can see Horovod. This is Uber's open source distributed deep learning framework for TensorFlow, which has at the time broken new ground in training speeds for deep learning models. When it comes to productionization, Uber has heavily invested in a deep learning as well as machine learning platform called Michelangelo. This allows us to utilize off-the-shelf algorithms, as well as these days also allows for us data scientists to deploy any Python code in a sandbox environment. When it comes to monitoring, this is a task that often both data scientists and developers are less excited about. To this end, we have built a fully automated real-time anomaly detection stack that I'm going to touch on a bit later, as well as an experimentation platform that allows for experimentation setup at scale. Now, of course, these tools and platforms have very greatly empowered us data scientists and analysts and have helped speed up the innovation cycle. But as mentioned in the introduction, we didn't want to stop there. We wanted to transform anyone in the company at a push of a button into a data scientist, of course, with best practices and guardrails incorporated. And this is where the platform teams come into play. These are deep domain experts in particular areas of data science, such as forecasting, anomaly detection, conversational AI, computer vision, or experimentation. I call them our data science ninjas. And together with their cross-functional counterparts, these teams build tools and platforms that then others can leverage across the company. And this allows us to multiply the expertise skill sets of these individuals across the company. So today I want to tell you about 3 areas of data science that we have been platformizing. The first area is the forecasting platform. Here, the vision of the forecasting platform is to provide highly accurate forecasts at a push of a button, without any forecasting expertise required. The only input needed by the end user is the historic data, perhaps in form of a query or a CSV file, and a forecast horizon, as in how far the user wants to forecast. And we do everything else automatically underneath the hood. I'm going to show you how. The output of this, as you can see here on this example, are point forecasts, as you can see in turquoise, as well as, of course, prediction intervals to get a sense of the uncertainty around the forecasts, as is shown here in yellow and red, respectively. These are very important to make actionable and informed business decisions. So one of the things we look at before we start platformizing is 3 criteria. The first one is, will this data science area, if platformized, yield step function improvements to the user experience? The second thing is, do we have a large number of use cases across the company that warrant the investment in platformizing this data science area? And then thirdly, across these use cases, are the modules that we're going to be building highly reusable? And the answer to both the forecasting platform as well as the other 2 areas that we're platformizing is a resounding yes. Here on this slide, I'm showing you 3 of the wealth of forecasting use cases that we have across the company. On the far left, you see marketplace forecasts. Here we are forecasting both supply and demand-related metrics at very fine granular spatio-temporal fashion. In the center, you can see real-time system outage detection use cases. The idea here is that we want to figure out as quickly as possible if there are any issues with the Uber app, such as people not being able to sign in, sign up, or perhaps not be able to take a trip. This is still an open research question due to a couple of factors. Firstly, the sheer amount of metrics. We have over 500 million time series. Secondly, the real-time nature of trying to detect such issues. We want to operate at 4.9, so 99.99% of availability, which gives us less than 1 minute of downtime per week. And thirdly, the high signal-to-noise ratio that we require, because these algorithms will page potentially people in the middle of the night, and nobody wants to be woken up just to find out that a Justin Bieber concert just finished. So we have to have extremely high precision and recall for these algorithms. We were able to break new ground in this field. And one of these systems that we have developed is to build dynamic thresholds, like you can see in the center graph here, that very closely follow the time series behavior, the day and night cycles, the underlying growth, as well as the variability. And for simplicity, I've then also added the data that came after the fact in blue here into this graph as well. On the very right-hand side, you can see the use case of hardware capacity planning. At Uber, we still have a lot of hardware on-premise, and so for us it is very important multiple months in advance to know highly accurately how much hardware to purchase as well as to provision. And this is particularly important for high-demand days, such as Halloween or New Year's Eve. This is also a very challenging problem, given how nascent our company is in terms of the number of years that we've been operating at, because many of these days are highly day-of-the-week dependent, and so we might have not seen them yet exactly under these circumstances. Again, here we were able to come up with completely novel algorithms that have broken new ground in terms of the accuracy of describing such special event days. And so therefore we are able to ensure that we're not over-provisioning hardware, which at the scale that Uber is operating at would be fiscally irresponsible, and at the same time ensuring that we're not under-provisioning, which could yield to an outage and lost trust of our riders and driver partners. So basically we need to have the Goldilocks principle applied, not too much and not too little hardware. So let's look at some of the steps that we have been tackling using our forecasting platform. The first step in every forecasting problem is to do data exploration and pre-processing. Now, pre-processing is an often overlooked step in forecasting problems and can be as important, sometimes even more important, than finding the right model architecture. To this end, we have built modules that automatically can detect and handle common pre-processing tasks. The next step is to identify which forecasting method to choose from. There are three major classes. On the left-hand side, you can see classical statistical approaches such as ARIMA or Holt-Winters. I've also included the less well-known theta method. We've found it to be very applicable to our time series. It is also a computationally very fast method, and it has won the international forecasting competition M3. On the right-hand side, you can see machine learning and deep learning approaches that more recently have entered the forecaster's toolkit. For example, we have found lots of success with quantile regression forest, the cousin of the well-known random forest, as well as deep learning methodologies such as LSTMs. The third category that is the most recent category that has emerged are hybrid methods. These are combinations between the classical statistical approaches on the left-hand side and deep learning approaches on the right-hand side. And one of our team members, Slavik Smul, has developed such a novel hybrid approach, and with this approach has won the international forecasting competition M4. Now, in a nutshell, it is impossible to forecast which of these methodologies will work best for a given forecasting problem. And so it becomes important to scan over a variety of different forecasting approaches to find the best one or the combination of the best forecasting approaches. And so I would like to talk a little bit about backtesting and the various different backtesting methodologies that we have implemented in our forecasting stack. Here it is important to note that chronological order in forecasts matter, and therefore also in backtesting. And so what one needs to do is take a specific series within the time series and train over that portion, and then test on the subsequent data. Now, keeping that in mind, there are two major approaches that I want to cover. On the left-hand side, you can see the so-called sliding window approach. Here you have a fixed window size of both training and test set. And as you move forward, you drop more historical data, as is seen in the light gray portion. On the right-hand side, you can see the expanding window approach. As the name suggests, Here, the training window size grows lag over lag, whilst the testing size typically stays constant. And this allows for great backtesting, especially if the time series data is short. Now, at Uber, we have developed a parallel language extensible backtesting framework that has both of these methodologies incorporated. And this now allows us to completely automatically scan over a wealth of different forecasting algorithms, such as the ones I've shown you on previous slides, and then to automatically surface the most accurate forecasts to our end users, of course with prediction intervals to get a sense of uncertainty. Here I'm showing a heat map. This is illustrative data that people can use to dig more deeply into some of the results if they wish. And we can slice, for example, by various different dimensions, such as cities, and then compare various different forecasting models to them. Now, these really cover the basic steps of any forecasting problem that we were able to semi-automate or fully automate. Now I want to cover some more advanced capabilities of this forecasting platform. The first one is being able to estimate the impact of special events, such as holidays, weather, concerts, and sporting events. As you can imagine, these can have very large impact on our supply and demand and other business metrics. And so in order to enhance the user experience, we want to have highly accurate estimates of the impact of such special events. Now, the classical statistical approaches that I've shown you on previous slides, we find them to be typically not very amenable to such problems, either because you cannot incorporate external factors at all, or if you can, they typically do not perform well. So we have heavily invested in both machine learning as well as deep learning methodologies. And here on this slide, you can see an example of one of the architectures that we have used. The first thing I want to call out in the spirit of automation is the pre-training step, which includes an encoder-decoder approach, which allows us to automatically extract various different features within the time series. We then concatenate the learned embedding with various different events data, such as weather, concerts, holidays, and other types of events, and then pass it through a prediction network, in this case a multi-layer perceptron, in order to yield the final forecast. In case you're interested in more details, we've also published a white paper on this topic, and the link can be found at the bottom of this slide. We have also ensured very high quality assurance on this platform. The first thing is, of course, the data that is flowing into the platform, as well as, of course, ensuring that we maintain high quality for any forecasts that we're distributing to our internal end users. We've also deeply integrated the forecasting platform into our data and infrastructure stack in order to allow for forecasts programmatically at scale. The second example of data science commoditization I would like to go into is natural language and conversational AI. And I would like to use as a concrete example here one-click chat, which is a recent product feature that we have launched in order to showcase some of the common aspects of conversational AI problems. So here in one-click chat, the purpose is to help connect riders and driver partners during the pickup experience, in particular to provide suggested replies to the user based on incoming messages that they're getting. And you can see an example of this on the far right-hand side. So let's look at one-click chat in the framework of a natural language problem. There are really two major steps here. The first one is, given an incoming message, for example, from a writer, we want to extract the intent or topic of conversation. Now, once the intent is found, we then retrieve various different replies that match this intent and surface it to the end user, for example, in this case, to the driver partner, where they can choose to pick one of those, for example. Now this seems like a very straightforward problem, but looking at it in practice, there are various different challenges that we're faced with. Firstly, these messages are very short. They also have abbreviations, misspellings, and also autocorrect is not our friend, as you can see from this real-world example at the bottom here. I'm Washington for you. This should clearly mean I'm waiting for you. So any method that we want to use here should not involve frequency-based methods such as TF-IDF, but rather should be able to capture the semantic meaning of the various different texts that we're getting. And so here we've used Google's Doc2Vec methodology in combination with nearest neighbors approaches and trained it on anonymized Uber data. And we were very excited to see that the example of I'm Washington for you is actually correctly classified then as I'm waiting for you. So as mentioned earlier, when we platformize, we're always looking for a wealth of applications across the company to help improve the user experiences. And so again, I would like to showcase to you a couple of the use cases that we have in this space. In addition to the one-click chat example that I've just walked you through, we also have been doing an alpha launch around hands-free dispatch. This allows now for driver partners to accept and reject trips using voice, and also the voice equivalent to one-click chat that will allow driver partners to free-form speak their responses to incoming rider messages. On the right-hand side, you can see our customer care use case. Here we have built an assistant that helps our customer service representative with various different tasks. Now, of course, the customer service representative will always have the final say here, but the natural language system helps understand what the intents are, can identify what the issue types are that people are writing in about, can make suggestions about which actions the customer service representative might want to take, and then also provides recommendations on which response templates the agents want to start off from when writing a response to the end user. We've seen over 8.8% reduction in average handle time, and of course this has also improved the user experience as a result. Here, a very high-level overview of the platform that we have been starting to build on this front. As mentioned, the majority of natural language conversational AI use cases would have as a first step intent identification, so the topic of conversation, and this is done by the semantic parser. Many conversational AI systems will have a back and forth component, which means we want to keep track of the state of the system, and this is done by the dialogue manager. And then finally, of course, we want to convert back the semantic representation into human understandable form, and that is done by the language generator. Now, the third and final example of data science commoditization and democratization I want to talk to you about is the most recent endeavor that we have been working on and that I'm personally very excited about. And that is semi-automating or fully automating exploratory data analytics at scale. So I'm sure many of you are faced with questions that you can see here on the left-hand side. At Uber, we're spending hundreds of human hours every week answering questions like these, or coming up with actionable business insights. Wouldn't it be amazing if you had a system that could automatically scan through the data and answer such questions? We have started to build such a system, and our proof of concept looks extremely promising here. But then we wanted to take it a step further. What if you didn't even have to ask the question in the first place? What if we had an algorithm that could scan through the data, surface interesting insights to business analysts, to our business stakeholders, who can then combine these insights with their business acumen to make actionable business decisions? And again, here we have built a proof of concept, and we've gotten really positive reviews from our internal users who have told us that we have been able to find various different insights that they would not have come up with themselves. So this would potentially give us an opportunity to scale data analytics and to be less dependent on the number of human hours that we can spend on this or the number of hypotheses that we can come up with. At the final stage of my presentation, I would like to walk you through our strategy of commoditizing data science. Because building platforms is a multi-quarter, multi-year initiative. And so it is really important for us to set our data scientists and platform builders up for success here. The approach that we have been taking is of 3 phases. In the first phase, we embed specialist data scientists into various different areas of the business. This allows us to get very interesting insights about the opportunities, the pain points, and that can have informed design decisions on the platform. It also allows us to solve use cases that are of great interest to the business and the user experience right there and then, and to build strong relationships that are trusting in nature with our stakeholders. Now, of course, this is not a scalable approach, and so we quickly go to building workflows or various different recipes that the broader data science community can leverage. For example, a Python notebook that is easily discoverable that people can build off from. And then the final step is, of course, to build these automated platforms that I mentioned that make anyone at Uber into a data scientist. And we do this by strategically choosing various different use cases that help augment the platform and reuse various different components of it. In case you're interested in learning more details about the work that I've presented today or about other areas that we have been commoditizing across the company, please check out our Uber engineering blog post. And with this, I would like to thank you very much for your attention.